Next, Zener diode. So in Zener diode, this is the Zener diode symbol. So here you will have two terminals, cathode and anode. This is the Zener diode available in the market. So here we are going to cover introduction, construction, working, application, and numerical of Zener diode. So in introduction, that is the Zener diode is nothing but it is a silicon PN junction device that differs from rectifier diode because it is designed for operation in the reverse breakdown region. The breakdown voltage of a Zener diode is set by carefully controlling the level during manufacture. The basic function of Zener diode is to maintain a specific voltage across its terminal within given limits of line or load change. Typically, it is used for providing a stable reference voltage for use in power supply and other equipment. So here they represented the symbol of Zener diode and also the basic Zener diode use to maintain 10 volt across the load. So construction of Zener diode. So here the Zener diode are designed to operate in reverse breakdown. Two types of reverse breakdown in a Zener diode are avalanche and Zener. The avalanche breakdown occurs in both rectifier and Zener diodes at a sufficiently high reverse voltage. So Zener breakdown occurs in a Zener diode at low reverse voltage. A Zener diode is heavily doped to reduce the breakdown voltage. This will cause a very thin depletion region. The Zener diode breakdown characteristics are determined by the doping process. Here, the Zeners are commercially available with voltage breakdowns of 1.8 volt to 200 volt. Then now we are going to see the working of Zener diode. A Zener diode is much like a normal diode. The exception being is that it is placed in the circuit in reverse bias and operates in reverse breakdown. This typical characteristics curve illustrate the operating range for a Zener. Note that its forward characteristics are just like a normal diode. You can look the characteristics of the Zener diode. Here after 0.7 volt in the forward bias region, the current starts increasing. Similarly in the reverse bias region, so after breakdown voltage, the current starts increasing in the opposite direction. So in this manner, the voltage, constant voltage is maintained. In the breakdown characteristics, you can see that the reverse portion of your diode's characteristics curve. When the reverse voltage is increased, the reverse current remains extremely small up to the knee of the curve. The reverse current is also called as Zener current. At this point, the breakdown effect begins. The internal Zener resistance, also called as Zener impedance, which begins to decrease as reverse current increases rapidly. So the Zener breakdown and avalanche effects are responsible for such a dramatic increase in the value of current at the breakdown voltage. If the impurity concentration is very high, then the width of the depletion region is very less. Less width of depletion region will cause high intensity of electric field to develop in the depletion region at low voltages. Let's take an example to understand things clearly. Let us say the width of the depletion region is 200 amps, but that is very small. If a reverse bias voltage of just 4 volt is applied to the diode, then the electric field intensity in the depletion region will be like this. Merely a voltage of 4 volt is responsible to generate an electric field intensity of 2 into 108 volt per meter. that is very high intensity. This electric field is sufficient to rupture the bond and separate the valence electrons from their respective nuclei. Larger number of electrons get separated from their atoms, resulting in sudden increase in the value of reverse current. This explanation was given by scientist C.E. Zener. So such diodes are called Zener diode. The Zener effect predominates in diode whose breakdown voltage is below 6 volt. Next, we are going to see the avalanche breakdown. So Zener effect predominates on diodes whose breakdown voltage is below 6 volt. The breakdown voltage can be obtained at a large value by reducing the concentration of impurity atom. We know that little amount of current flows in the reverse biased diode. This current is due to the flow of minority charge carrier, that is electrons in the p-type semiconductor and the hole in the n-type semiconductor. So the width of the depletion region is large when the impurity concentration is less. So when reverse bias voltage is applied across the terminal of the diode, the electron from the p-type material and the holes from the n-type material accelerates through the depletion region, which will result in collision of intrinsic particles like electron and holes with the bound electron in the depletion region. With the increase in reverse bias voltage, the acceleration of electron and holes also increases. Now the intrinsic particles which collides with the bonded electron with enough energy to break its covalent bond and create an electron hole pair. This is shown in the figure. Avalanche breakdown mechanism is shown in the figure. You can see the collision of electron with the nuclei. When electron hole pair created, the diffusion of electron from p-type material also you can see it. So the collision of electron with the atom creates an electron hole pair. This newly created electron also gets accelerated due to electric field and breaks many more covalent bonds to further create more electron hole pair. This process keeps on repeating and it is called carrier multiplication. The newly created electron and hole contribute to the rise in reverse current. The process of carrier multiplication occurs very quickly and in very large number, that there is apparently an avalanche of charge carrier. Thus, the breakdown is called avalanche breakdown. Now we are going to see the difference between Zener breakdown and avalanche breakdown. So here main differences are nothing but here heavily doped with a narrow depletion layer. In avalanche breakdown, lightly doped with the depletion layer. This breakdown voltage sets a very strong electric field, but here it is not strong enough. Then here electric field is very strong to rupture the covalent bond, thereby generating electron hole pair. So here large number of current carriers will have. Here minority carrier collide with the semiconductor atoms in the depletion region, which breaks the covalent bond and electron hole pair or generator. So newly generated charge carriers are accelerated by the electric field, which result in more collision and generates avalanche of charge carrier, which will be resulting in the avalanche breakdown. Here it exhibit negative temperature coefficient in the Zener breakdown, but here it will exhibit positive temperature coefficient. This is the PN junction breakdown characteristics, as I said earlier. This is the Zener diode characteristics, electrical characteristics, maximum rating, symbol value, unit, everything are given here. This is ideal model and ideal characteristics curve of Zener diode. This is practical model and ideal characteristics curve of Zener diode. Now we are going to see the Zener diode application. So here Zener regulation with a varying input voltage. Zener diode can be used for this purpose. So as the input voltage increases, the output voltage will remain constant. Even though the input voltage decreases, the output voltage also remain constant. That is the use of Zener diode in this application for regulating the voltage. Next, Zener limiting. Here, Zener diodes can be used in AC application to limit voltage swing to desired level. The numerical of Zener diode. So here a Zener diode will exhibit a certain change in voltage for a certain change in current on a portion of the linear characteristic curve between the IZK and EZM, which is represented in the diagram. Then temperature coefficient of the Zener diode changes their percentage based on the Zener voltage for every change in temperature, that is represented by the formula del Vz equal to Vz into Tc into del T. So here are some examples they represented. You can refer it. See, this is the few example of using Zener diode in the circuit. You can also see, look over it. So Zener diode voltage will produce a single stabilized voltage output. Here it can be connected together in series along with the normal silicon signal diode to produce a variety of different reference voltage output value also. So the value of individual Zener diode can be chosen to suit the application based on our needs. The supply voltage Vin must of course be higher than the largest output reference voltage. So here we had seen the types of, so far we had seen the Zener diode, how it is operated, what is the structure, and then how it is acting as a current limiting resistor and voltage regulator. So here we can design the Zener diode as a voltage divider to maintain a constant DC output voltage across the load in spite of variation with the input voltage changes in the load current. So the stabilized output voltage is always selected to be the same as the breakdown voltage of the diode. Thank you.